Welcome to this presentation on three key concepts in number theory: Euclid's division lemma, prime factorization, and irrational numbers. By the end of this video, you'll have a solid understanding of these important topics and how they are used in mathematics. Before we dive in, let's quickly go over the objectives for today. First, we'll explore Euclid's division lemma and how it's used. Then, we'll look at prime factorization, one of the fundamental building blocks of number theory. Lastly, we'll discuss irrational numbers and some famous examples. Let's get started. We begin with Euclid's division lemma. This is a mathematical statement that says if you take any two positive integers, a and b, you can express a as the product of b and another number q plus a remainder r. The important thing to note here is that the remainder r is always less than b. In simple terms, it's a formal way of describing division with a remainder. Let's break it down with an example in the next slide. To illustrate Euclid's division lemma, let's take 13 and divide it by 3. Using this method, we can say that 13 equals 3 times 4 plus 1. 1, where 1 is the remainder. Here, a is 13, b is 3, q is 4, and r is 1. This equation fits the condition of the lemma because the remainder is less than the divisor b. This process can be used for any two positive numbers. Now, let's see how this lemma is applied. One of the main applications of Euclid's division lemma is finding the highest common factor, or HCF, of two numbers. This is done using the Euclidean algorithm, which involves applying the lemma repeatedly. For example, to find the HCF of 30 and 12, we first express 30 as 12 times 2 plus 6. Then we apply the lemma again to 12 and 6. The process stops when the remainder is 0, and the divisor at that point is the HCF. In this case, the HCF is 6. Now, let's move on to prime factorization. Prime factorization is the process of breaking a number down into its prime factors. A prime number is a number greater than 1 that can only be divided by 1 and itself. Prime factorization allows us to express any composite number as a product of prime numbers. For example, the number 60 can be factorized as 2 squared times 3 times 5. Let's look at an example on the next slide. Here's how you can find the prime factorization of 84. First, divide 84 by the smallest prime number, which is 2. We get 42. Then, divide 42 by 2. We get 21. Then, divide 21 by 3. We get 7. Then, divide 7 by 1. We get 7 2 again to get 21. Since 21 is not divisible by 2, we move to the next smallest prime, which is 3, and divide 21 by 3 to get 7. Since 7 is a prime number, the factorization stops here. So, the prime factorization of 84 is 2 squared times 3 times 7. Prime factorization is incredibly important for several reasons. It's used to find the HCF and LCM of numbers. It also has applications in cryptography, where large prime numbers are used to encrypt data securely. Another key concept is the unique factorization theorem, which states that every composite number can be written as a unique product of prime factors. Prime numbers play a crucial role in many areas of mathematics and technology. Next, let's talk about irrational numbers. An irrational number is a number that cannot be expressed as a ratio of two integers. In other words, you can't write an irrational number as a fraction. The decimal expansion of an irrational number is non-repeating and non-terminating, which means the digits go on forever without forming a pattern. Famous examples include the square root of 2, which is approximately 1.414, and the number pi, or pi, which is approximately 3.14159. Let's discuss some properties of these numbers. Irrational numbers have some interesting properties. First, their decimal expansions never repeat and never end. Second, when you add or subtract a rational number and an irrational number, the result is always irrational. The same goes for multiplication and division, as long as the rational number isn't 0. For example, 2 plus the square root of 3 is irrational, and the square root of 2 times 3 is also irrational. There are a few famous irrational numbers that appear frequently in mathematics. The most well-known is pi, which is the ratio of a circle's circumference to its diameter. Another important irrational number is the square root of 2, which is the diagonal length of a square with side length 1. Finally, we have Euler's number, e, which is used extensively in calculus and exponential growth models. Let's quickly compare rational and irrational numbers. Rational numbers can be expressed as fractions, while irrational numbers cannot. Rational numbers have decimal expansions that either terminate or repeat, while irrational numbers have non-repeating, non-terminating decimal expansions. For example, the number 1/2 equals 0.5, which is rational, while the square root of 2 is irrational because its decimal never ends and has no repeating pattern. To summarize, Euclid's division lemma helps us divide numbers and find their HCF. Prime factorization allows us to break down composite numbers into prime factors, which is useful in many areas of mathematics. Finally, irrational numbers, which can't be expressed as fractions, have fascinating properties and are an essential part of number theory. I hope this presentation gave you a clear understanding of these important concepts. That's all for today's video. If you have any questions or want to explore these topics further, feel free to leave a comment below. I'll be happy to help. Thanks for watching, and don't forget to subscribe for more math content.